In previous segments, we've documented the rapid growth and evolution of mesoscale convective systems through multiple stages and their position in the hierarchy of important weather and climate building blocks. In this section, we'll take a closer look at their life cycle. We'll then introduce a graphical representation that will enable us to identify distinctive features within a mature MCS. That will become a tool we use in the subsequent video segment where we describe the data sampling requirements for advancing MCS study and how TropSat will contribute. To review, tropical mesoscale convective systems are highly dynamic weather events that grow and evolve rapidly through multiple stages. As the name implies, they extend over a large area, sometimes covering hundreds of square kilometers. They pump significant moisture into the Earth's atmosphere and scale upwards to larger and longer-lasting atmospheric building blocks that exert strong influence over global weather and climate. As a prelude to dissecting their life cycle, we'll start with convection itself. Convection is a fundamental mechanism of heat transport in the atmosphere. Broadly defined, convection is the vertical movement of a fluid when heated from below, and it occurs in all fluids where a heat source exists. This includes water in a kettle, air surrounding a wood stove, and even the liquid rock within the Earth's mantle. Because of concentrated heating by the sun, convection in the tropics is a constant condition. The disorganized popcorn convection we've described previously represents the baseline state. It generates the familiar feels of low-flying, puffy cumulus clouds associated with tropical latitudes. Popcorn convection is contained in the planetary boundary layer. Recall that the boundary layer is the lowest layer of the atmosphere, the layer directly influenced by contact with the Earth's surface. The boundary layer rises and falls on a daily cycle. It's deepest in the afternoon when heating and convection are highest. Generally, it does not extend upward more than 1,000 meters. For the most part, winds are turbulent in the boundary layer and more laminar above. The first stage of MCS development occurs when individual popcorn convection plumes intensify and push warm, moist air through the boundary layer into the lower levels of the free atmosphere. That's indicated by increasing vertical scale on the left. Moist air absorbs heat more efficiently than dry air. When the free atmosphere is colder and drier than the tops of the popcorn convection plumes that have pushed through the boundary layer, those can go through secondary heating. Due to elevated heat content, they become buoyant relative to the surrounding cooler, drier air, and they begin to rise. As they do so, they also cool and moisture condenses out as rainfall. If the temperature difference between the rising moist air and surrounding atmosphere is maintained at altitude, the vertical movement, or updraft, can be rapid and sustained, leading to formation of much taller convective columns that appear as boiling cumulonimbus clouds. When this deeper convection occurs, rainfall is intense and a thunderstorm may develop. For scale, a typical thunderstorm in the tropics is a few kilometers on a side. Where deep convection is sustained, it can extend to and even slightly through the top of the troposphere, which you can see here with the vertical scale increased further. It's worth noting that while both popcorn convection and the individual deep convective plumes we've described so far are below the detection limit of TropSat, the MCS precursor conditions surrounding them are not. Those conditions and the instrumentation for sampling them will be reviewed in the next video. In this segment, we're focused on the building block hierarchy, and upwards in scale from individual plumes is where we find mesoscale convective systems. MCS develop when multiple deep convection plumes cluster together over a large area. Where individual plumes may be a few kilometers on a side, that dimension in a fully developed MCS may be 100 kilometers or more. At this scale, the MCS life cycle lends itself well to tracking and measurement from space. Indeed, the MCS images we've been using were taken from the International Space Station. And it's from here that the upscaling to the progressively larger building blocks we've discussed continues. It continues to superclusters of MCS embedded in the active phase of the Madden-Julian oscillation, to spin-off events that push horizontally out of the tropics and into higher latitudes, like atmospheric rivers and tropical cyclones, and even further to multi-year phenomena like the El Niño Southern Oscillation. Again, it's the physical processes by which MCS develop, grow larger, and aggregate upward in scale to more consequential weather and climate events that are a primary focus of the TropSat mission. Having arrived at the mature phase of MCS development, we'll lean on the work of Professor Robert Howes next to identify important physical characteristics within those systems. Virtually all refereed papers on MCS from the last 25 years cite Professor Howes, and most use some variation of this schematic from his research. We'll build our own version of the drawing, first to call out those key physical characteristics, and in the next video to identify data acquisition requirements for studying the MCS life cycle. The schematic is an MCS cross-section. It illustrates both large areal extent and, in this instance, movement direction to the left. Out ahead of the MCS, there are individual popcorn convection cumulus clouds indicating high moisture content. At the surface, within the boundary layer, air is flowing into a gust front where wind speeds pick up. The most dynamic zone within an active MCS is the squall line region that forms right behind the gust front. This is where warm, moist air from the surface gets pulled into strong updrafts. It's the area of deepest convection. The air cools rapidly as it rises. The drop in temperature condenses the moisture, causing areas of most intense rainfall and largest raindrop size. The strong updrafts within the squall line are characterized by convergence in the surface wind field. Above the squall line region is where cloud tops penetrate highest into the atmosphere, so also where those cloud tops are coldest. Behind the squall line is the stratiform region. In this zone, rainfall is widespread but much less intense. There are often areas of subsidence or descending air. Those are characterized by divergence in the surface wind field. We'll use this same cross-section diagram to describe the final or decay phase of the MCS life cycle. In some ways, MCS sow the seeds of their own destruction. Their huge cloud shields and the latent heats of evaporation and condensation occurring over fast timescales and large areas cut off or counteract the heat source that drives their development. In their decay phase, MCS detach from the boundary layer. Surface wind convergence dies down and updrafts weaken. Precipitation from stratiform regions ceases. Rainfall at the leading edge of the MCS continues but tapers off in intensity. This wind down proceeds until we end up back at the original baseline atmospheric state in the tropics. That default state is the disorganized and shallow popcorn convection that's contained below the boundary layer. Thanks for viewing this section on the MCS life cycle. It provides an indication of the data requirements for understanding their dynamics more clearly. In the next segment, we'll cover how that data is acquired currently, the gaps that exist, and how TropSat would impact that data record.